This module of my videos deals with a very quick review of linear systems. And in the previous videos on that, I talked about the time domain analysis. And the Laplace transform was a significant tool used there. And this little relationship here was a significant result of that, which says the output of a system in the Laplace domain is this product of the transfer function of the system and the Laplace transform of the input. Now we're talking steady state. What does that mean? For one thing, it means as time goes to infinity. Another thing, we mean the output of the system does not go off to infinity. It remains bounded, even as time goes to infinity. So we need to restrict what systems we're talking about and what inputs we're talking about. And for one thing, we're going to limit ourselves for this analysis to stable systems. As for inputs, you could look at inputs such as a unit step, ramp, acceleration, constant acceleration. Those latter two, those inputs become unbounded. So if the system follows it, it becomes unbounded. You could look at maybe the error between the input and the output. And there, in steady state, as time goes to infinity, one of three things happen. Either that error goes to zero, it goes to some non-zero constant, or it goes off unbounded. And if you're really interested in that, we would use the final value theorem of Laplace transforms. We don't talk about that in this course. It's in my control systems course. So what we're going to be looking at is stable systems where the input involves frequency of some kind. So we'll start off with phasors. Here's the input f, e to the imaginary number, where this omega is the frequency in radians per second of that phasor. Here's the Laplace transform of a phasor. So if you use this basic relationship, here's what the output is in the Laplace domain. Going from there up to here, if you use partial fraction expansion, it would break down this. It's a over s minus j omega plus a bunch of terms that are due just to the transfer function. When you translate this back into the time domain, you get this. This comes from that first term, and then all these mode functions, this linear combination mode function, come from this QS. But if the system is stable, as time goes to infinity, all these guys go to zero. And all that takes is for all these lambdas, all these poles of the system, for their real parts to be strictly negative. So in steady state, output of a stable system where the input is a phasor is this guy. It's the same frequency as the input. And what is this A? I won't go through this derivation, but it is just the transfer function itself where you plug in j omega for s. That's pretty amazing. And by the way, I'm not going to go through all the derivations for this. Look at my textbook on this on my website. I'm just kind of outlining things. So then, because we're talking linear systems, sinusoids are just a simple linear combination of phasors, right? Cosine is what? 1/2 e to the j omega. And the sine is, or plus e to the minus j omega. Similarly for a sine. So since it's linear, the linear combination of inputs yields the same linear combination of the individual outputs to those inputs, so that we can find what's the output when the input is a sinusoid. And there we get a similar result. In steady state, meaning as time goes to infinity, the output is a sinusoid with the same frequency as the input. And it turns out the only thing different then is the amplitude of this output sinusoid and the phase of this output sinusoid. And it turns out you can compute both of them from the transfer function itself. Again, the gain, or this ratio between the amplitudes of the input and output, is this magnitude of the transfer function, and the phase is this inverse tangent of this ratio. We're not going to go much beyond that in this course, but that's all pretty interesting. For more, again, see my control systems. And for more derivations, go to my website. From there, we can generalize even more, because I'm not going to go through this derivation in any detail. But again, because it's a linear system, the output of a linear combination of a bunch of inputs is the same linear combination of all the outputs to those same individual inputs. So we can express an input signal first as a whole bunch of phasors. And you get the Fourier coefficients. You're basically taking the Fourier series. And then you could do it over an infinite number of frequencies. Fill up the entire real line of Fourier coefficients, and you get the Fourier transform. I know I did some hand waving there. I'm just outlining the derivations. But the big result then is this relationship now in the Fourier domain. This X is the Fourier transform of the output. This F is the Fourier transform of the input. These arguments, which are frequencies, not just S. You know, in the Laplace domain, S didn't really mean anything to us physically. Now these arguments have physical meaning. They're frequencies. This guy in general would be the Fourier transform of the transfer function. But since in my course, I only talk about causal systems, and when that is the case, this G is actually the G we found using Laplace transforms, where we now plug in J omega for S. And all this assumes that the input has a Fourier transform. So we're kind of restricting things even more. So finally, we get to the thing that, at least in my course, is all we're really going to look at in the frequency domain for certainly linear system, deterministic linear systems. And by the way, this whole module is deterministic. There's no random variables or random processes involved in this module. But anyway, they have defined the power or average power of a signal. It's kind of based on the physics of things, or I should say they got the idea from physics, but there's no direct physical meaning here. They just came up with a definition of what the power of a signal means. And there's some theorems that say that power is spread out over time, but it's also spread out over frequency. And whatever's in this integrand here, by definition, is called the power spectral density. It's how the power of the signal is spread out over frequency. So now let's take a little break, because I haven't said, how do you get that thing? Here's the definition of the autocorrelation function of a deterministic signal. In the previous module, we talked about autocorrelation function of a random process. Here, it's a deterministic signal. It's this thing. F is a function. You have another tau. Shift of that, you multiply the two together. Anyway, you integrate all that. That's called the autocorrelation function. Without going through the derivation, the power spectral density is the Fourier transform of that autocorrelation function. So now we have a way to calculate the power spectral density of a signal. And here's the bottom line. Again, I hand waved my way through the derivations. I'm not even attempting that in this video. But the big thing is we can relate output power spectral density to input power spectral density by this relationship. Here's the output spectral density. Here's the input spectral density. I just need to calculate this guy here, which is the magnitude of this thing squared. And you have all these relationships where power spectral density is the Fourier transform. Well, power spectral density of the inputs, the Fourier transform of the input, power spectral density of the outputs, the Fourier transform of the output. And then you can recover autocorrelation functions by inverse Fourier transform. Get to an example next time, which is kind of where the real meat of this is. All we're really going to do in this course is look at these autocorrelation functions and power spectral densities. I'll do the example in the next video.